Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over the Chatelier's principle, and here are a few examples I'm going to be going over. So first, again, the Chatelier's principle is basically that a system in equilibrium is going to readjust itself in order to counteract a disturbance in the system itself. Anything that disturbs that equilibrium is going to shift in such a way as to reduce that stress or reduce that disturbance. So, so I'm going to go over several examples that go over different types of ways of stressing or disturbing the system. So you could do that by adding product or taking product away. You could add or subtract reactant. You can increase or decrease pressure if you're working with gases in your system, or you could be raising and lowering temperature if you've got an exothermic or endothermic reaction. So in that case, when you have an endothermic or exothermic reaction, you're treating the heat released or absorbed as a product or reactant, and I'll talk about more about that in a moment. So let's do the first problem. So here, the first one is you have calcium carbonate solid goes to calcium oxide and CO2. So then they're asking what would happen if you added CO2, carbon dioxide. So here, when you add the carbon dioxide, you're increasing the amount of carbon dioxide. So the system is going to want to decrease that amount you added. And so it's going to shift in the way that's going to reduce the stress, reduce the amount. It wants to try to get back to where it was. Now, it's not going to get there all the way. It will get back to equilibrium, but the equilibrium concentrations will be different. So that means if I add CO2, if I add stuff here, then it's going to shift in this way so that carbon dioxide or product is converted to reactant. So you're going to decrease the product and increase reactant, and so that's going to get it back to equilibrium. So the shift, we say shift to the left or shift towards reactants. If you add calcium carbonate, that is a reactant. So here, if you add a reactant, what's going to happen is you're going to increase this concentration. The system is not going to like that. So now you've got too much reactant. So so now you're not in equilibrium anymore. So now the system wants to get back to the equilibrium. So since you added reactant, it's going to want to get rid of that reactant and make more product. So it's going to go in this direction. So it's going to shift to the right. And so then it'll increase the products. All right, what about number 2? So in number 2, you have 2 BRNO. That's going to go to 2NO and Br2, bromine. So here it's asking, for this example, what happens if you add BRNO or add Br? If you add BRNO, this is a reactant. Again, you're going to increase the amount of reactant, so now it's not going to be at equilibrium. And the equilibrium is going to want to shift to, the reaction is going to shift to go back to equilibrium. Well, in order to go back to equilibrium, you got to get rid of some of that reactant you added. So it's going to shift this way and go towards the reactants. So the other way you can think about this as well is think about it in terms of your K value, right? Your equilibrium constant, right? You've got some amount A over some amount B. So remember, A is your product, B is your reactant. So if I add more reactant, right, that means I'm increasing the denominator, decreasing the ratio. But so that means now I'm no longer at equilibrium. So in order to get back to what the K constant is, now it's too small because I increased reactant. So now I need to make it larger. I need to get back to what K was. So if I add reactant and now the whole thing, the ratio is smaller, that means I got to decrease the denominator, increase the numerator so I can get back to what the K value is. So that's another way to view this from a mathematical point of view. So if I add reactant, I'm going to shift this way to get rid of the reactant and increase product to get back to equilibrium. If I'm adding product here, now I'm adding product, so I'm adding the top part, so the numerator is getting bigger, and so it's going to want to, so if the numerator gets bigger, then this whole thing is bigger than it should be. It's going to be bigger than Kc. So it's going to shift to get back to Kc, so it's got to shift smaller. That means it's got to reduce the product, increase reactant. So it's got to go this way. So it's going to shift towards reactants. Number 4. Here we have gases and we're looking at volumes. What's going to happen when you increase or decrease volume? So that also has to do with pressure too. So what's going to happen is, let's take reducing volume. If I decrease the volume, and if you think about Boyle's law, remember Boyle's law is the volume of a gas and the pressure of a gas are inversely proportional. So if I'm decreasing the volume, then the gas particles are going to hit the sides of the container more often because there's less surface area, there's more space or less space between the molecules. So they're going to hit the container more often, and therefore they're going to increase the force, that the overall force on the inside of the container, the force being applied by the particles, and therefore it's going to increase pressure because pressure is equal to the force divided by the surface area of the container. And so what's going to happen is if I decrease volume, pressure goes up, and then the system is going to want to release that pressure. And the way that it can do that is by decreasing the number of particles involved in collisions. So if I decrease the volume, I'm increasing pressure. So in order to decrease pressure, I have to switch, I have to shift to the side with less moles. So less moles means less particles. So here I have, now solids don't count here, so you're not counting solids or liquids, only gases. So here I have 3 moles of oxygen gas, here I have 2 moles of solid, and here I have solid. So since I have 0 moles of gas over here, and I have 3 moles of gas over there, it's going to shift into this direction to release or relieve that stress or that pressure. So it's going to lower the pressure. What if the volume goes up? Well, if the volume goes up, it's the opposite effect. So volume is to get bigger. There's going to be less collisions because there's more space, there's more surface area. So there's going to be less collisions on the sides of the container at any one time, and that's going to decrease pressure. And so in that case, if you're increasing the volume and decreasing pressure, now you want to increase that pressure back up to where it was at equilibrium. And so what you're going to do is you're going to shift towards the side with more moles of gas. So I have 0 on this side, 3 on this side, so it's going to shift in that direction. What if I have an inert gas? So a gas that is not part of the reaction. Then that's not going to have any effect whatsoever on the equilibrium. It's not involved in the reaction. It's doing nothing. So you don't have to worry about inert gases. And the other reason is Dalton's law of partial pressures. So the sum of all the pressure in the container is equal to the total pressure. So individual pressures are not going to affect each other because gas particles are so far apart. According to the kinetic molecular theory, they're not going to influence each other. They don't have attractive forces, even though they really do. And in this situation, those attractive forces do not really, they're negligible. They don't really play a part. So we don't have to worry about that. Quickly, what about number 4? So same thing. If I lower the volume, I'm going to increase the pressure. So I want to go in a direction where I want to decrease that pressure. So I want to switch to the side that has less moles of gas. So I have 2 moles of gas over here, and I have 3 moles over here. So I'm going to switch. I'm going to go in this direction to lower the number of moles, the particles of gas, and that's going to reduce the pressure. So I raise the pressure by, decreasing the volume. So now I want to decrease that pressure, and the way that it's going to do it is by switching to the side with less particles, less moles. Again, if I increase the volume, increasing the volume is going to decrease pressure. If I decrease pressure, that means in order to reach equilibrium again, got to get that pressure back up. I got to go in the direction that's going to increase the pressure. So I'm going to go in the direction that's going to increase the number of particles. So here's 3. So here's 2. Here's 3. So I'm going to go in this direction to increase the number of particles, which is going to increase the pressure and get back to where equilibrium was. Number 5. Now we're looking at temperature. So really quickly, we're going to treat the heat that's evolved or released or gained by a system as a product. That's the best way to understand it, the easiest way to understand it. So here, it's an endothermic reaction. That means that heat is being absorbed. So heat would be a reactant. So I got to put heat in here. So heat is a reactant. Endothermic, I got to put heat in to get the reaction to go. So in this case, if heat is a reactant, then when I raise temperature, raising the temperature is like putting heat in. So I'm adding heat. If I'm adding heat, that means I'm adding a reactant. So if I'm adding a reactant, it's going to shift to kind of get rid of that reactant. So it's going to shift in this direction. If I'm lowering the temperature is like taking heat away. So if I'm taking heat away, I'm taking the reactant away, and then it's going to shift to replenish what was lost. So it's going to have to shift in this direction to replenish the heat that was lost. So that's how that works with temperature. And finally, you have number 6. Same thing. In this case, it's an exothermic reaction. So since it's exothermic, that means heat is evolved, it's released, it's produced. We're going to treat it as a product. And so in this case, if you raise temperature, that means you are increasing the heat. You're adding heat, right? Raise temperature, you're adding heat. If you're adding heat, you're adding a product. If you're adding a product, then to get back to equilibrium, you got to get rid of some of that product. So it's going to go towards the reactants. And then if you lower the temperature, it's the opposite effect. Lowering the temperature takes heat away. If you're taking heat away, you're taking a product away. To replenish that product, it's got to go in this direction to make more product. So I hope this was helpful. If you like this video, please like, share, subscribe, hit the notification bell. Thanks for joining me. I'm Mr. Cobalt. See you next time.